Hello everyone, this is Srikash here with my teammate Shashank. This is the video for homework 2 for the course Design and Analysis of Reconfigurable Systems, and today we will be demonstrating working of 32-bit LED counter on Intel Cyclone V FPGA. First off, open Quartus and create a new project. Here I already created the project, so I'm just gonna open it. In the files, as you can see, we have added the Verilog design. This is a general 32-bit counter implementation which updates on passage of the clock and asynchronously resets at negate of the reset pin. Additionally, there is a direction pin that indicates the counter to count up or down depending on the user input. Lastly, assign the last 4 MSB bits of the counter to 4 output pins so that we can observe the output at LEDs. Now go to the designs, select the top level and hit compile. After compilation is done, as you can see in the analysis and synthesis and resource usage summary, the total number of ALMs needed are 17, the combinational AL logic usage is 33, and dedicated registers are 32, with IO pins of 7. After compiling, go to Assignments, open Pin Planner, and assign the pins to the necessary pins on the board. Here, as you can see, we are assigning our output pins to the respective LED so that we can observe the LED blinking on the board. Now close the pin planner. Now going to the timing analysis, open timing analyzer. Go to custom reports and report timing. As you can see, the slack is positive from node internal counter node 0 to 28 bit. And to report critical path, report path. The maximum delay obtained is 6.366 nanoseconds and the max operating frequency is 1 over 6.366 nanoseconds. Now upload the generated SOF file using program device open programmer to upload to the FPGA board.
Yeah, so once we are done with our pin planning, go ahead and close this. So we have to dump our program into FPGA board now. To do that, connect the FPGA board using the cables given to your device. Click on program device on the left side. You're going to pop up this window. To set up our device, click on hardware setup. Click on correctly selected hardware drop down menu. So let me go ahead and connect the board. So as you can see, once I connected the board, it's going to detect like DE1-SoC USB 1. Select that and press close. Now click on auto detect. Click on the device. Since we are using 5SC SEMA5, click on that. Now click OK. So as you can see, it already detected everything. Now what we have to do is we have to load our bitstream file, the .sof file, into to the FPGA board. To do that, go ahead and select this one. Right click on that. Click on edit and click on change file. Go to output files. Click on ledCounter SOF and click open. Now click on enable the program configure button. Once you do that, it's going to enable the start button. Click on start. Now it's going to load the whole bitstream file onto the FPGA Cyclone 5. So as you can see, the whole dumping is successful. It indicates the good into success.
Yeah, once you have dumped our program onto the board, as you can see, the sequence has already been started for the 4 MSB of the debit counter output sequence. So let's first study what is the output we are getting. So this is the output we're going to get for the 32-bit counter. So we're only popping out the 4 MSB of the values. So it is like triple one, double one, double one, triple one zero. It's going to start decrementing like that. So as you can see on the board, so this is the reset button. Once I click this, it's going to roll over to the maximum value, double one, that is FFF value. Now it's going to start counting down from there. It's triple one zero is 14. Now it's going to be double one zero one is 13. And now double one double zero is 12. As it's going to count down like that. Once I change this direction button, it's going to start counting up from that position. It's like double one zero one now, 13, triple one zero 14, all ones with the 15. So as you can see, depending on the direction button and the input given, the sequence has been either incrementing or decrementing. This indicates that we have successfully programmed our board using our ledCounter counter, only printing out the sequence of the 4 MSBs, depending on the direction button we desire.
For the second part of the assignment, assign the last top 10 bits from the counter to the LED out pins. Then go to hierarchy, select your design and hit compile. After synthesis is done, as you can see in analysis and synthesis, in the resource usage summary, the total number of ALMs, combination ALU to dedicated logic registers are equal to the previous example. Now open the pin planner and assign the necessary pins according to the board pin descriptions. Here, as you can see, we have assigned our LED output 10 bits to the respective pins on the board so that we can see the LED blinking on the board. Now close the pin planner. Recompile the design after assigning the pins from pin planner. Open timing analysis, open timing analyzer and report path. Here the maximum delay is 6.645 nanoseconds from counter node 28 to LED output of 6. So the maximum frequency is 1 over 6.645 nanoseconds. Close timing analyzer and open program device to open the programmer and flash the design to the FPGA.
Yeah, so once we are done with our pin placement, it's going to generate this .qsf file as you can see here. So you can either edit this file or go ahead and just directly edit on the pin planner. Either way works. Now once we are done, go ahead and close this and resynthesize the whole design again. Once you have done that, we have to dump our program onto the FPGA board. To do that, click on program device. So as you can see, the board has been already detected for our previous project 4 MSB output. Now, but we have to change our output file depending on the 10 LED counter. So now right click on this board, click on edit, click on change file. Now go to output files, click on 10 LED counter.sof, click open. Now it's going to load the whole new output file. To program that into our board, enable the program configure button and click on start. So as you can see, the dumping has been successful.
So once we have dumped our program onto the Cyclone V FPGA board, it's going to start processing. So as you can see, the output sequence has been already being generated. So first let us study the output, then we can go ahead onto the board output sequence. Now let us study the output sequence. So as you can see here, these are the 10 MSBs that are being printed using the LEDs on the FPGA board, like 15, 14, 13, everything. So once I click the reset button on this board, it's going to start from all Fs. It's going to count down from FFE, FFFD, FFFC. So those values are going to be start printing. If I change the direction button, now it's going to start counting up. Like if it is like at 1010, the A is going to go to B, C, 1100, then D 1101. So the fast flickering is because of the rapid change of the values at the 4 MSB, the final output sequence. Since the 010116 sequence is like rapidly changing, that is the reason we can observe the fast flickering of on the LEDs here. Let's do it once more. Click on the reset button. It will reset to the bounce back to the maximum value all once. I think it's at like some changing value at, I guess, 4, FFF4. Now if I change the direction, it's going to start counting up from the same value. Since the flickering is very fast, we can't note the change, but it does do that. So finally we have successfully programmed our FPGA using the 32-bit ledCounter to print out the 10 MSB values.
So once we have successfully completed our board testing of 32-bit ledCounter, we have to store the FPGA configuration file into the flash memory. So with the previously generated .SOF file, it will automatically download in the SRAM of the board, but it implies that once the board is turned off, it's going to lose the information. So to avoid that, we have to load that into flash memory. So in that way, it can be stored indefinitely onto the board. To do that, we have to convert our SOF file to JIC file. So go ahead and click on File and select Convert Programming Files. Select the programming file type as JIC. Set the configuration device as EPCS128. The mode is active serial. Select the file location. Now load the file by clicking on this and click Add File. So I'm going to go ahead and select the ledCounter file. Click OK. Wait until it loads, and now we have to select the device which has the flash memory that it is intended. Click Flash Loader and click on Add Device. Go ahead and select the Cyclone family, Cyclone 5, then scroll down and select 5 and click OK. Once check the settings and everything, once everything looks good, click on Generate. Click on Yes. So yeah, as you can see, the output file has been generated. Yeah, so once we have generated the .gic file, so we are ready to program the flash memory. To do that, before we have to select our MCell to the bit stream 10010 on the FPGA board. So I went ahead and done that. So open the GUI of the Quartus Prime, go to Tools, scroll under to Programmer. You click on Hardware Setup and select the DE1-SoC board and click Close. If nothing pops up, just click on Auto Detect. Select the device 5C SE-MA5 and click OK. So as you can see, the program has been loaded. It is detecting the board. Once we have done that, we need to upload a .gic file to our board. So to do that, double click on this None, select the file, upload _file.gic, it's a JTAG file, click Open. So it's going to show this EPCS128 thing. Once we are done with that, enable the programmable configuration button and click Start. Wait until it uploads. As you can see, our file is loading onto the FPGA board. Yeah, as you can see, it's done. So that indicates that our file has been stored onto the flash memory and it can be retained onto the board. Thank you.